Hello friends, in this video I'd like to solve the following problem from the Romanian District Mathematical Olympiad for 12th graders 2006, problem number 2. Let us define these two sets. Set G consists of all the matrices 2 by 2 but with complex entries whose such that the absolute value of the determinant of A equals 1, and let H be the subset of G which consists of matrices 2 by 2 matrices with complex entries whose determinant is 1. We wish to prove that G and H are multiplicative, so they are groups with multiplication, but they are not isomorphic. It's a very nice problem. Again, a bit hard for 12th graders, but it is what it is. Here are my hints. Well, showing that they are groups is rather trivial if you know the property that determinant of two matrices can be written as product of determinants. But to show that they are not isomorphic, we need this notion, or the easiest way is to use the notion of the center of a group. Center of a group is the set which consists of all the elements which commute with every other element of our group. And if two groups are isomorphic, then they share the exact same algebraic properties. In particular, their centers should be equinumerous. They should have the same number of elements. Now, the rest of the problem is to show that our groups G and H their centers are not equinumerous. Namely, you should show that the center of G has more than 2 elements, while the center of H has exactly 2 elements. The first part is easy. The second part is harder. To show that the center of H has only 2 elements, take any matrix in H and consider what are the constraints on A, B, C, and D for which, for example, this upper triangular matrix commutes with our matrix, and when this lower triangular matrix commutes with our matrix. And after all of that, you should be able to establish that our two groups are not isomorphic, sorry. So give this problem a try, and I will see you in just a minute. All right. So let's maybe start with showing that they are groups. Well-known fact. It's a well-known fact. I don't remember the exact name of this theorem, but determinant of product of two matrices is the product of determinants. Which means that if, for example, if the absolute value of A equals the absolute value of determinant of B equals 1, then the absolute value of determinant of AB is also 1. Similarly, if just determinant of A and just determinant of B are 1, then determinant of AB is also 1. Also, determinant of identity matrix is 1. And also, since determinant, or if determinant of some matrix is not 0, then this matrix is invertible. And moreover, determinant of this inverse matrix is 1 over the determinant of our matrix A. In particular, if this is 1, this is also 1, or if this has the absolute value of 1, this also has the absolute value of 1, which all these facts mean that G with multiplication and H with multiplication are groups. All right. Now, I will consider centers. First, I will show that center of group H has only 2 elements. Do that. Notice that, well, in the center of our group, for sure, there is minus a identity and identity. They are for sure in the center of H. In fact, it's also in center of G. Well, why is that? Because of, if you take any matrix A, and if you multiply it by the identity, you get just the identity times A. Similarly, A times minus identity is the same as minus identity times A. Because, alright, so at least two elements are in our centers. I will show that in center of H, there is no more elements. How can we do it? Well, suppose that some matrix A, B, C, D is in the center of our group H. Then the following 3 conditions must be met. In particular, maybe let's write it as that. In particular, if we take upper triangular matrix and now multiply it by ABCD, it should be exactly the same as ABCD times 1, 1, 1, 0. Notice also that the determinant of upper triangular matrix is 1, so this matrix is in our group H. And also it should be the case that if I take lower triangular matrix, it should also commute with my matrix ABCD. All right. So it's a necessary condition for matrix ABCD to be in the center. Not sufficient, but necessary. You will see that that suffices. So let's multiply everything. In the first row, we will have A plus C, C, B plus D, D equals, and on the right hand side we have A, C, A, C, A plus B, C plus D. And for the lower equation, we'll have, this time we have A plus C, then B plus D equals A plus B, C plus D, B, D, if I am not mistaken. All right, now let's compare. This should be equal to that, so we immediately can conclude that C has to be 0. What else? Let's take a look. Here we have A, here we have A plus B. So B must be 0 as well. And what else? Let's take a look. Well, for example, here we have B plus D, here we have A plus B. So for this to be true, A must be equal D. And remember also the determinant of our matrix A, B, C, D is 1. Just determinant. Just the determinant of A, B, C, D is 1. i.e., we have one more condition, AD minus BC must be equal 1. And let's consider all of that. Our matrix, in fact, I can substitute AD is the same as A, here we have 0, here we have 0. So this condition really says that a squared equals 1. And how many solutions do we have of this equation? Well, just 2 solutions. A is either minus 1 or 1. So we have only 2 elements in our center. So center of H consists of only minus I, which corresponds to minus 1, and of the identity matrix, which corresponds to 1. No more elements in the center of our group. Alright, and what about the center of G? Well, we don't even have to find the exact cardinality of center of G. Let's just notice that identity minus identity are for sure in the center of G. And let's find one more matrix, which for sure is in the matrix of our group G. But also I, 0, 0, this matrix is also in the center of G. How do I know it? Well, let's take a look. What's the determinant of this? The determinant of this matrix is I times I, which is minus 1. The absolute value, remember we are in G, talking about G right now, the determinant, the absolute value of minus 1 is 1. So this matrix really is in our group G. Does it commute with every other matrix? Yes, it does. If A is any other matrix in G, then notice the following, that A times I, 0, 0 is the same as A, I, the identity matrix, and since this is just a number, it can be put in front. So it's E times I, but if I do it in the other way, it's E, A, again, it's EA. It's exactly the same. Which means that for sure the cardinality of G, the center of G, is at least 3 or more. And finally, we can deduce that since the cardinality of center of G is greater than or equal 3, and cardinality of center of H is 2, from these two facts, we can already say that these two groups are not isomorphic. They cannot be, because isomorphism transfers all algebraic properties of it, maps center of one group onto the center of other group. So there is no bijection from set with more than 2 elements onto the set of 2 elements. There is no such bijection. And that closes our proof. It's a nice way of proving that, in general, when showing that 2 algebraic structures are not isomorphic, it's good to locate some algebraic property, purely algebraic property, which is not carried over from one group to another. For example, cardinality of center or something else, or number of solutions of some polynomial equation. In this case, looking at centers was crucial. Thank you very much for watching. I hope that you've learned something in this time. And I will see you next time. Goodbye.